Hello engineers, welcome back. In this video, we're going to practice graphs again using another lead code question. Okay. So first let's try to understand the question and then we'll see how we can approach this, right? So this is an easy problem. It says find if path exists in graph, right? So there's a bidirectional graph with n vertices where each vertex is labeled from 0 to n minus 1 and n minus 1 is inclusive. The edges in the graph are represented as a 2D integer array edges where each edges of I equal to ui vi denotes a bidirectional edge between vertex ui and vi. So ui and vi are the source and destination of the edge. Every vertex pair is connected by at most one edge and no vertex has an edge to itself. Okay, so if there is a edge between a pair, that is the only edge that can be possible. You want to determine if there is a valid path that exists from vertex source to vertex destination. Given edges and integers n, source and destination, return true if there is a valid path from source and destination or false otherwise. Okay, so let's understand this with this example. So there are three vertices here, n equal to 3, and then there are three edges. So first edge is between 0, 1, so that is this edge. Second edge is between 1, 2, that is this edge, and then 2, 0, that is this edge. So they have given source as 0 and destination is 2. So we need to determine if there is a path between 0 and 2. As you can see here, there is a direct edge. So the answer is true. Okay. So there are two paths from vertex 0 to vertex 2. From 0, we can go to 1 and then to 2, or we can directly go to 2. So we can go from 0 to 1 and then 1 to 2, or we can directly go to 2. So this is an undirected bidirectional graph, right? So that's why if there is an edge between 0 to 2, so it means that there is also an edge between 2 to 0. So it's a bidirectional graph. Okay. Let's see this example. This is a disconnected graph. So there is 0, 1, 2 and then 3, 4, 5. And our source is 0 and destination is 5. So we need to check if there is a path between 0 to 5. As you can see, there is a disconnect between the two sets of vertices. So the answer is false. There is no path from vertex 0 to vertex 5. Okay, so that's what we need to answer. So let's see how we can approach this. Let's take this example. Okay, now we have this graph and we need to find out if there is a path between 0, 2. So the source is 0 and destination is 2. We need to check if there is a path between 0, 2, right? There are multiple ways in which we can solve this question, and we are going to use breadth first search for this. Okay, we can also solve this with depth first search. We can also solve it with disjoint sets and so on, right? But we are going to solve with breadth first search as a practice, and I will leave it to you to explore the concept of disjoint sets and how we can use disjoint sets to answer this question, right? So we already know how to use breadth first search. We already discussed this in our BFT video. Okay, so quick recap, what do we need? First, we are going to make an adjacency list like this with our given graph, and from there we are going to take two things, a queue and a visited array, and we do breadth first search. So it means that we start at one node and then explore all the neighbors and then move on to the next node and explore all the neighbors, right? So we start at 0, we explore 1, 2, and then we go to 1, explore the edges of 1 and so on. So we will apply the same concept here. So we'll make an adjacency list first. So how will that look like? So this is the adjacency list. So from 0's point of view, there are two edges, 1, 2. From 1's point of view, there are two edges, 0, 2. And 2's point of view, there are two edges, one is going to 0 and another one is going to 1. Okay. So we will also need a queue and a visited array. So how will the traversal look like? First, we start at 0 and push it to the queue. And then we explore all the edges. So we add 1, 2 to the queue. We pop it and add the children, add the neighbors 1, 2. And then we go to 1 and mark it as visited as we go along. So initially the visited vector is all false, and as we go along the queue, we mark them as visited. So 0 is visited, and then we go to 1, 1 is visited. And if there are any children to 1, they will get added to the queue if they are not already visited, right? So 0, 2, 0 is already visited and 2 is not visited. So 2 is added to the queue. Now 1 is visited. And then we have 2 in the queue, but 2 is already visited. So nothing to do, right? So this will be our general breadth first traversal, right? So as we go along this traversal, we will look for source and destination. That's it. So our starting point will be the source and we will keep looking for destination. If we find a destination, we will return true. Otherwise, we will go through the entire graph, and if there is still no destination found, we will return false. Okay. So it's a simple exercise. Let's see how we can code it. So first let's take our ingredients. What do we need? First we need to build our adjacency list. So let's take a new vector. What will be the size of this vector? It will be of size n, the number of vertices, right? And then everything will be an empty vector to begin with, right? Now let's fill this adjacency list. For this, we will go through this array. This is where the edges are. So we go through this array, we go to the first edge, and then we have source and destination here. So we add it to the adjacency list like this. So what is the data type of each edge? It is a vector of int. Okay, we are looping through the edges. Now we are at the first edge. So what is the first edge? It has two things, 0th index and first index. There are two pieces in this. So all we need to do is adjacency list of edge of 0 dot push back edge of 1 and repeat the same thing. So what is happening here? In the adjacency list, we are making this list. Okay, so we already have these three in the adjacency list, which are empty vectors. Now we are filling these values. So what is the first edge? 0, 1. So adjacency list of 0, which means here, dot push back the destination edge of 1. And similarly on the other side, from 1's point of view, we are adding 0. So this is what is happening here. We are building the adjacency list. Now we will use the breadth-first traversal technique to see if we can find the destination. So first we will implement the traversal. So for that we will need two things. First we will need a queue, and then we will also need a visited array, which will be vector of boolean, which will be of size n, and everything will be false to begin with. Okay, so we will add our first element to the queue, which is our source, given source. Okay, and let's mark this as visited. Visited of source is true. This is visited. Now let's do the traversal. While queue not empty, first we will get the element out. Once we have the element, we can pop it. Now we can check if this element is our destination. If front equal to destination, then nothing to do. We can happily return true from here. Otherwise, we will add the neighbors. For neighbors, we will go to our adjacency list. For int neighbor, which is in adjacency list of front. So we are checking if this is visited or not. If neighbor is visited, nothing to do. Otherwise, we will add it to the queue, queue.push neighbor, and we will mark it as visited. So this is our typical breadth-first traversal, and this is the additional step. If we find our destination, we will stop our search here. And if we go through the whole loop and still we haven't found our destination, it means that there is no path between the source and destination. We can simply return false from here. And that's it. Let's run and see. Accepted. Let's submit. And it is accepted. So what will be the time complexity? Since we are just doing typical breadth-first traversal, it is the same time complexity as our breadth-first traversal discussion, which is O of V plus E. So that is the solution. So as I said, this can also be solved using depth first search. It can also be solved using disjoint sets. But at this point of time, we have kind of explored all the fundamentals required for data structures and algorithms. And there is a lot more in data structures and algorithms. There are so many algorithms, so many combinations in which questions can be made, and the structures can be altered to use more effectively, right? So that is it for this video, guys. Thank you so much for watching. If you have any questions, definitely ask me. Don't forget to leave a like if you found this helpful. Don't forget to bookmark the playlist. Don't forget to comment if you have any questions or suggestions. Thank you so much for watching. I will see you in the next one. Cheers.